Thank you. Okay, so lastly we're looking at hybridization in carbon, and we saw that we can have sp3, sp2, and sp hybridization. And as a reminder, carbon starts in its ground state configuration, its lowest energy configuration, the one that's predictable from the off-ball Pauli exclusion and Hund's rule, as 1s2, 2s2, 2px1, 2py1, and 2pz0. We saw that that doesn't account for the tetravalence of carbon or any of the bonding features of carbon, so carbon gets excited. We move an electron from the lower energy 2s into the vacant 2pz. That requires the input of two different sets of energy. The energy required to unpair the electrons against their magnetic attractions. Right? Remember, clockwise spinning electron generates one pole of a magnet. The anti-clockwise spinning electron generates the antipode. And so together there's a magnetic attraction that is superimposed and stronger than the electronic repulsion. And that's what keeps the electrons together. So I must now uncouple the electrons, right? Break the magnetic attraction, and then provide a small amount of energy to bridge the 2s2p gap. So this is an excited species, that is 1s2, 2s1, 2px1, 2py1, 2pz1. Now, what happens from here depends upon the bonding of the carbon. So if you have a molecule like this, I have a species like this, and I ask you to give me the hybridization states of all of the carbons in that molecule. What you will do is you will ask, how many pi bonds, if any, is the carbon atom forming? That's the first question. Now, and I've said this before, very often in organic chemistry, as in life, the question you're asked, or the problem you're solving, is not really the one you're answering, right? So the question you're asked here is, what are the hybridization states of the carbon atoms? That's the question. You must get at the question behind the question. And the question behind the question is, first of all, how many pi bonds is the carbon forming? Or how many pi bonds do the carbon atoms form? Because that will inform you as to how many p orbitals the carbon atom needs to reserve for pi bond formation. Because remember, pi bonds are formed exclusively by p-p overlap, right? And it must be side-on. So if I look at this carbon, let's start with this one. This carbon is forming 4 bonds, right? 1, 2, 3, 4. That's a sigma bond. That's a sigma bond. Because all sigma bonds are sigma, which we'll talk about in a second. One of these is sigma and one is pi, and there's no convention as to which one is sigma and which is pi. It doesn't matter. If I label this one as sigma, then that one must be pi. If I label this one as pi, then that one will be sigma. But in any multiple bond, one is sigma, the others are pi. So this carbon is forming one pi bond. It must therefore reserve one p orbital, let's say 2pz, for pi bond formation. It'll hybridize the remaining s. Remember, we don't mess with the core electrons. It'll hybridize the s with the 2 remaining p's, and this will be sp2 hybridized. What about this carbon? Well, it's not forming any pi bonds. Therefore, it doesn't have to reserve any p orbitals, right, for pi bond formation. It will mix the s with all 3 p's and the sp3 hybridized. That carbon is forming 2 pi bonds. It must therefore reserve 2 p's, right, for pi bond formation. It will hybridize the s with one of the p's, with the remaining p, and the sp hybridized. That will be true for both of these carbons. Oops. Let's make this a fluorine, shall we? What about this carbon? Well, it's forming 1 pi bond, so it must reserve 1 p orbital. It'll hybridize the rest and be sp2. And that's true also for that carbon. Seriously? This carbon is forming 1 pi bond. It will reserve 1 p orbital for pi bond formation. It will hybridize the remaining 2, and it will be sp2 hybridized. This carbon is forming 2 pi bonds. 1 to this carbon, 1 to that carbon. And so it's going to keep 2 p orbitals reserved. It will hybridize the remaining 1 and be sp hybridized. This carbon is forming 1 pi bond. And therefore it'll be sp2 hybridized, right? It'll keep 1 reserved for pi bond formation and hybridize the others. Oh, and so is this one. So this is also sp2 hybridized, right? 1 pi bond keeps 1 p orbital reserved and hybridize the rest. It's sp2 hybridized. Okay, that's the carbons. If you notice, I've got heteroatoms on the board. I've got 2 oxygens, I've got an N, and I've got a fluorine. And I want to know what is the, and I also have hydrogens, which aren't heteroatoms, we'll get there in a second. And I want to know what are the hybridization states, if any, for the non-carbon atoms in a molecule. Let's start with H. So H is not a heteroatom, but it's a non-carbon atom. So let's get the hybridization state, if any, of the hydrogens. Well, if you remember in the energy diagram, we have energy on the axis, and I have energy level 1 and energy level 2. I've got the 1s, I've got the 2s, and then the 2p's. Hydrogen has 1 electron in the 1s energy level. So what does it require for me to hybridize orbitals? So for orbitals to hybridize, right, to mix, 2 conditions must be met. We must say that the orbitals have to be similar in sizes and similar in energies. So for orbitals to merge, right, for orbitals to overlap and hybridize, for orbitals to hybridize, they must be similar in energy and similar in size. We can say then that those orbitals have to have what's called complementarity. So for hybridization to occur, the orbitals must be complementary to each other. In other words, the orbitals in the 2s and 2p energy levels are similar in energy, right? The gap between 2s and 2p is not massive, so there's a similarity in energy. And the 2s and 2p in size are similar. I mean, the s is smaller, but it's not massively smaller than the 2p. However, in the 1s, in the first energy level, there are no other orbitals beyond the 1s. So there's nothing else for the 1s orbital to mix with. There are no partners in the first energy level. And of course, the gap between 1s and 2s is significant, so they would not be complementary because the energy gap is too big. And remember, for them to overlap, to hybridize, they must show complementarity. Right? They must show complementarity, which means similar energies and similar sizes. So if you are an element in the first period, in other words, H and helium, you can't hybridize. There are no partners in the first energy level to the 1s. The 1s is alone in the first energy level. So if I ask you what's the hybridization state of H, you will tell me it doesn't have one. The H doesn't hybridize, right? It simply overlaps, undergoes chemistry via its 1s orbital. So H can't hybridize. Okay. So what about the other atoms, the other non-carbon atoms? Let's look at the heteroatoms. So let's look at O, for example. So, well, in fact, let's do nitrogen, because nitrogen is next to carbon. So in the electronic configuration for nitrogen would be, so this is carbon. For nitrogen, it would be 1s2, 2s2, 2px1, 2py1, 2pz1, right? Nitrogen has 1 electron more than carbon, so it's 2pz1, right? Instead of 2pz0, it's 2pz1. But what happens next for nitrogen? Well, whereas carbon promoted a 2s electron into the 2pz, which it did so it could maximize the number of bonding options, right? You can form 4 bonds rather than just 2. In nitrogen, there is no gain in doing so. If I promote a 2s into a 2p, I'll still have 3 unpaired electrons. Right? So with nitrogen, there is no promotion step. There's no energy, there's no excited step. All nitrogen will do is hybridize from here. Right? So carbon underwent excitation first to go from 2 unpaired electrons to 4. With nitrogen, I have 3 unpaired electrons. If I take one of these and pair it here, right? I'll have 1, 1, 1. I'll still have the same 3 unpaired electrons. So there's no value to promoting. So when nitrogen hybridizes, it hybridizes from that configuration. Well, what will it do? Well, how many pi bonds does this N form? And the answer is, it forms 1. Therefore, it will reserve 1 p orbital for pi bond formation to the carbon, and hybridize the s with the remaining p's. Does that sound familiar? So this nitrogen, like the carbon that's attached to, is sp2 hybridized. What is the hybridization state of this O? Right? Well, the configuration for O, the ground state configuration of O, is 1s2, 2s2, 2px2, 2py1, 2pz1. Right? O has 1 electron. O has 1 electron more than nitrogen. Right? Because it's carbon, nitrogen, oxygen across the periodic table. So, again, there is no value in promoting anything. Oxygen will hybridize from here. So, what's the hybridization state of this O? Well, how many pi bonds does the O form? It forms 1. So, it's going to keep the one of the p's reserved for pi bond formation, the p that has a vacant, has 1 electron, so you can overlap to form a bond. It reserve 1 p for pi bond formation, and hybridize the s, the 2s, with the remaining p's, and the sp2 hybridized. So the rules don't change whether we're looking at hybridization in carbon, nitrogen, oxygen, sulfur, it doesn't matter. Okay? If you're not forming any pi bonds, you're sp3. If you're forming 1 pi bond, you reserve 1 p for pi bond formation, there are 2 left, those 2 overlap with the 1s, with the 2s, and they become sp2. If I'm forming 2 pi bonds, then I will reserve 2 p orbitals for pi bond formation. I will have 1 left. It will overlap. It will hybridize with the s to form an sp. And it's exactly the same rules for carbon, nitrogen, oxygen, and so on. And why is that? Because they all have access to the same set of orbitals, an s and 3 p's. But I can detail this in a different way. Or in fact, let's do this over here. How many pi bonds? So this N was sp2. How many pi bonds is this O forming? The answer is none. And therefore, I don't need to reserve any p orbitals for pi bond formation because I'm not forming any. I will therefore hybridize my s with all 3 p's and and I'll be sp3 hybridized. Okay? And again, hybridization is a good thing because hybridization, when it happens, makes the orbitals all have s character. So the orbitals are smaller, which means the bond is shorter and stronger. Okay. What about the fluorine? Well, ordinarily, what I would say is the fluorine has no unpaired electrons. I'm sorry. The fluorine forms no pi bonds. Good God. The fluorine forms no pi bonds. Therefore, with F, I'll have 1s, well, I'll put it here. F as 1s2, 2s2, so 1, 1, 1, and then back again. So it's 1s2, 2s2, 2px2, 2py2, 2pz1. So this F is forming no pi bonds, so it doesn't need to reserve any p orbitals. So what I would guess is that the F would hybridize the S with all three p's and be sp3 hybridized. It turns out it doesn't. So whereas hydrogen cannot hybridize because there are no other orbitals other than 1s in the first energy level, there's nothing for it to play with, the halogens choose not to hybridize. And why is that? The reason is if the halogens were to hybridize, what would happen? And the answer is the orbitals that they use to bond would get very short, would get very small, because they have s character. The bonds would get very short. If the bonds got very short, what would happen is the distance between these lone pairs and, for example, the bond pairs in the carbon would get shorter and shorter. So you can imagine here's a carbon, and it's doubly bound to a carbon here, it's bound to another carbon here, and it's bound to the fluorine. So if this bond, if the fluorine bonds via an sp3 hybrid, this bond gets short, which means the distance between these electrons and these and those gets shorter. So there's a lot of repulsion. Because remember now, the fluorines, I'm sorry, I said that wrong. If the bond is short, if the orbital the fluorine uses to bond is sp3, then this bond will get short. If the bond gets short, it means that the lone pairs of electrons on the fluorine get closer to the bond pairs of electrons that the carbon has. And the closer that distance, the more is the repulsion and the more unstable is the species. So what fluorine does instead is, in order to minimize the repulsion, it chooses not to hybridize. That way, if I bond via the P, that's exciting, if I bond via the P, then this carbon F bond is now this long, and therefore the lone pairs of the fluorine are further removed from the bond pairs in the carbon. And so the force of repulsion is now lower. Okay? So the halogens, although they can, because it's got S and P's, the halogens choose not to hybridize. And when the halogens bond, they bond via the p orbitals. And it's just an effort to minimize repulsion. Because ordinarily, hybridizing is good because it makes the orbitals small. Small orbitals lead to short bonds. And ordinarily, you want your bonds to be short because short is strong. The problem is, if your atom, like the halogens, has a lot of lone pairs, and you make the bond short, you bring those lone pairs in proximity to other bond pairs in the molecule. And the repulsion between those now raises the energy. So the short bond would stabilize you, but the proximity of the lone pairs to the bond pairs would destabilize you. And the destabilization is greater than the stabilization. Okay? Okay. So I'm now going to ask you, we're not going to, so the halogen is not hybridized. Okay. So I'm going to ask, I'm going to do two things. I want to get an inventory of all the bonds and all of the valence electrons in this species. So all of the valence electrons, which really will include all the bonds as well. So I'm going to ask, what orbitals, what is the nature of this bond, and what are the orbitals that make it up? What are the orbitals that comprise the bond? Well, the bond is a single bond. The single bond is sigma. I'll get to that in a second. So I'm going to say that is a sigma bond, and it's made up of the s orbital of a hydrogen and the sp2 of a carbon. All right, remember we said this was sp2. Okay? What about this bond? Well, that bond is a single bond, therefore it's a sigma bond, because all single bonds are sigma. It's a sigma bond that's made up of the sp2 of a carbon, seriously? The sp2 of a carbon and the sp3 of another carbon. What is the nature of this bond? Well, I could designate it as either sigma or pi, because the other one would be the other. So let's call it sigma. It's made up of the sp2 of a carbon and the sp2 of an O. If that one is sigma, then the other one is pi, and that's made up of P of the oxygen and P of the carbon. Remember, all pi bonds are caused by, or formed by, pp overlap. What is the nature of this bond? Well, that's sigma bond, because all single bonds are sigma. It's formed by the sp3 of a carbon and the s of an H. And it doesn't matter who I put first. I could have said s of H and then sp3 of carbon. The sequence doesn't matter, just who they are. This bond would be sigma, sp3 of carbon, sp of carbon. This bond, one of them is sigma, the rest are pi. I'm just going to pick the bottom one as sigma. It'll be sigma, sp of carbon, sp of carbon. And then these two will be pi, p of carbon, p of carbon. Sigma, sp of carbon, sp2 of carbon. Sigma, sp2 of carbon, p of fluorine. Right? Draw that one in. This is sigma, sp2 of carbon, p of fluorine. Let's call this one sigma. Sigma, sp2 of carbon, sp2 of carbon. That means this one is pi, p of carbon, p of carbon. Sigma, sp2 of carbon, sp3 of O. Sigma, sp3 of O, sp2 of carbon. Sigma, sp2 of carbon, s of hydrogen. Sigma, sp2 of carbon, sp of carbon. Pi, p of carbon, p of carbon. Pi, p of carbon, p of carbon. Sigma, sp of carbon, sp2 of carbon. And so on and so on and so on. So I could designate the character of every bond, sigma or pi, and tell you who are the component orbitals. Okay. What I also want to do, though, is look at the lone pairs. And I want to ask, in which orbital are those lone pairs housed? Right? In which orbital are the lone pairs housed? And that's kind of what I just did. I said that this bond pair is housed in a sigma orbital formed by s of hydrogen and sp2 of carbon. And these orbitals are sigma and pi. They are molecular orbitals. So they will have two components, right? Because that molecular orbital encompasses both the hydrogen's nucleus and the carbon's nucleus. These orbitals, however, are atomic. So in what orbitals are these electron pairs housed? Well, let's see. So remember we said with O, this carbon was sp2 hybrids, right? So what does that mean? I'm going to ignore the 1s because that's not involved in hybridization. If I'm sp2 hybridized, I'm going to leave the pz alone for hybridization, for p orbital formation, for pi bond formation, and I'll hybridize these. So what would I get? I've got 1, 2, 3 orbitals. That's going to give me 3 hybrids. And they have 1 part s and 2 parts p. So it's 2 sp2, 2 sp2, 2 sp2. And I'll have the unhybridized 2pz. Okay. There were 2, 4, 5 electrons in atomic orbitals. And when they hybridized, those 5 electrons need houses. Where are they? I'll go 1, 2, 3, Hund's rule, and then double up 4, 5. Okay? So what happens? I'm going to use the unpaired pz to form the pi bond with the carbon. So the orbital on the O that forms the pi bond with the carbon is, for my diagram, the pz. That takes care of that electron. The sp2 hybrid on the O is going to overlap with the sp2 hybrid on the carbon. That will form the sigma bond. That takes care of that unpaired electron. That leaves me 2 pairs in sp2 hybrids. That's these. In other words, if I know the hybridization state of the atom, I know 2 other things. I know the designation of the orbital that the atom uses to form all of its sigma bonds. So if I am sp3 hybridized, all of my sigma bonds will utilize an sp3 hybrid from me. So carbon uses the sp3 hybrid to form that bond, that bond, that bond, that bond. If I am sp2 hybridized, all of my sigma bonds will be formed by me using an sp2 hybrid. So this was sp2 of the carbon. This is sp2 of the carbon. This is sp2 of the carbon. So if I know the hybridization state of the atom, I can tell you what is the designation of the orbital the atom uses to form its sigma bonds. But I can also tell you in what type of orbital any lone pairs the atom has are housed. So if I'm sp2 hybridized, my lone pairs are housed in an sp2 hybrid. Because those are the orbitals available. Okay? What about this O? Well, that O is in a slightly different scenario. That O forms no pi bonds, which has to be 3 hybridized. So what I'm going to do is I'm going to hybridize the S. I'm going to hybridize the S with all of the P's. I'm going to form 4 sp3 hybrids. So 2 sp3, 2 sp3, 2 sp3, 2 sp3. I had 2, 4, 6 electrons. Where do they go? 1, 2, 3, 4, double up, 5, double up, 6. I'm going to use 1 sp3 hybrid to form this bond. That's the sp3, so this bond will be sigma, sp3 of the O, sp2 of the carbon. So that's this one. This bond is sigma, sp2 of the carbon, sp3 of the O. That's this one. I'm now left with 2 lone pairs. Yeah, that one and that one. So those lone pairs are housed in sp3 hybrids. So if I know the hybridization state of the atom, that is the same designation for the orbital in which the lone pairs are housed, and for the orbital I use to form my sigma bonds. So if I look at this and I ask you, in what orbital is this lone pair housed? All I have to ask is, what's the hybridization state? If it's sp2 hybridized, they're housed in an sp2 hybrid. End of story. Okay. Okay. All right. So what we're going to do is ask and answer two more questions related to hybridization. And one that we mentioned earlier is that all single bonds are sigma. Let's talk about it really fast. So the halogens I say fluorine bond by the p orbitals. So let's assume that those two fluorine atoms are going to bond. How would they bond? What would their preference be? Well, one option is that they overlap side-on and form a pi bond. So maybe they overlap this way and give a fluorine-fluorine pi bond that would look like this. Okay? That's one option. The other option is that they will orient themselves so that the p orbitals point towards each other collinearly, in which case what I get is this. So which of the two would be preferred? Let's think it through. If I did this, it means here is my nucleus of my fluorine, here's the nucleus of the fluorine. There is nothing here because the p orbitals overlap above and below, which means I'm going to be exposing my fluorine nucleus to my other nucleus. The repulsion here is going to be massive. Repulsion destabilizes. The bond will fly apart. And although I have electrons technically in the internuclear gap, they're not exactly between the nuclei. So not only have I increased my force of repulsion, my force of attraction is not that great because the swell of electron density is far from the nuclei. So when the two atoms overlap, if I form the pi bond, that's not really a good scenario. But if they overlap end-on to form sigma, the nuclei don't feel each other, certainly not as much, because they're buffeted by the electrons in the internuclear gap. So my force of repulsion is low, right? Because the nuclear repulsion, they don't feel each other. The electrons run interference. Plus, my force of attraction is huge because my nuclear electron distance is short. So if I'm going to form a single bond, that single bond is going to be sigma, where I make the orbitals overlap end-on. It doesn't matter what the orbitals are. It could be p and s, or sp2 and sp3, or p and p. It doesn't matter. If I'm going to form a single bond, it's going to be sigma. That way I maximize attraction and minimize repulsion. So all single bonds are sigma. Now, obviously, if I form a sigma bond, if I need to form another bond, I can't block the space in the middle. I can't use the space bang smack in the middle. That's already occupied. Which is why all further bonds go up here and down here, up high, or they come out and back. Right? So if I had, like in the case of the alkynes, once I form the sigma bond, so I occupy the space between the two nuclei, my next bond is going to go above and below. That's the pi bond. The next is going to go out and in. That's a triple bond now. And at that point I'm stuck. Because remember, they don't just go up and down, out and in. They make a cylinder. In which case all the space between the nuclei are occupied. Bang smack between them and all the way around them. Which means I can't have more than a triple bond. The highest bond order I can have is 3. Because at that point there is no more space between the two nuclei. Okay. The last thing we'll ask with hybridization is, if I asked you to give me an example of a pure orbital and a hybrid orbital. Well, my pure orbitals are S and P. In other words, they have only a single letter, a single designation. They are either S or P. Those are pure orbitals. My hybrids would be sp2, sp3, sp, spd2, and so on, sp3d2 and so on, like in sulfur. Which brings up another interesting question. So I'm going to ask you to give me an example of a bond formed by pure overlap, pure hybrid overlap, and by hybrid overlap. So give me an example of a bond that's formed by pure overlap, by pure hybrid overlap, and by hybrid. So pure would have to be an S and an S. For example, hydrogen. So H, this is one S and one S. That's a pure. Okay? Or a pi bond, any pi bond. Right? Pi bonds are formed by PP overlap. So PP overlap. So for example, let's say this bond, the pi bond in a carbonyl species. What if I wanted, or HF? HF would be a 1s and a 2p. So that's an sp overlap. What if I want a pure hybrid? A pure / hybrid overlap? Well, that's going to require either an S or a P overlapping with an sp something. So for example, I could have this one. This is a pure hybrid overlap. S of a hydrogen, the sp2 of a carbon. Or this one, S of a hydrogen, sp2 of a nitrogen. P of a fluorine, sp2 of a carbon. And so on. So this will have to be a P or S with an SPN. Hybrid would then be an SPN. So this one is the sp2 of a carbon, sp2 of an O. That's a hybrid. This one, sp of a carbon, sp2 of a carbon. Hybrid. The last thing that just occurred to me is, so we are pretty much focused on hybridization in carbon, but as you know, hybridization can occur in any number of elements. So I mentioned briefly a second ago the sp3d2. All I would ask you about that in organic is how many hybrids would that give me? Well, how many interacting orbitals were there? 1s, 3 ds, 2 ds. So that's 1, 4, 6. So I would get 6 hybrids. What percent S character would they have? It'll have 1 part of 6 S character, 3 parts 6, 3 parts of 6 P character, 2 parts 6 P character. Okay, so that's 50%, 50% P, 33 and 30% D, and what? 16.25 whatever percent, 0.5, 16 and a third percent S. And so you could get that sort of a question as well. Okay, so at this point, we're done with hybridization. So we can identify which atoms hybridize, which ones can't, which ones don't, and hopefully explain why. we can look at a molecule and tell the nature, we can tell what are the hybridization states, if any, of the atoms in the molecule. We can identify the types of bonds, sigma or pi, what are the component orbitals in each bond, and if there are lone pairs, we can say what kind of orbital the lone pair is housed in. Okay. So what we're going to do is look at representations of organic molecules. And there are three common, well, there are three ways of representing organic molecules. Two of them are more common than the other. And quite frankly, once we go through this topic today, I will only be using one of them moving forward. So let's say I ask you to draw, because we were drawing isomers earlier, let's say I ask you to draw, let's say this compound. So this is what we would call a dash structure. This is what's called a dash structure. That's the one you've seen me draw all semester so far. It shows all bonding pairs of electrons as dashes. Okay? There is also a dot structure, which is very rarely used. And this time, a dot structure will show all of the bonds as shared electron pairs. So this would look like H. It's my O. So these two electrons represent that bond, these two that bond, these two that bond, these two that bond, and so on and so on and so on. When it's a double bond, I show my 4 electrons between the C and the O. A lot of people say these look like Lewis structures on drugs or something. In a dot structure, you can or cannot complete the Lewis structure to do this. Right? You don't have to. In the same way, in the dash structure, you could or could not put in the lone pairs to complete the Lewis structure. It's optional. You rarely see this dot structure. You see the dash structure a lot, with or without the lone pairs, the Lewis structure. What we will do moving forward is use really neither one of these. We're going to use what's called the bond line structure. What the bond line structure does very cleverly is it says we're going to represent carbons as points, and we're going to show all the heteroatoms in the molecule, but none of the H's, with one exception, which we'll talk about in a second. We're going to show the carbons as dots. We're going to show all the heteroatoms, but none of the H's attached to, I didn't say that, none of the H's attached to carbon, with one exception. So we're going to show the carbons as dots, as points, all the heteroatoms, none of the H's attached to carbon, with one exception, but we will show H's that are attached to heteroatoms. So how would I draw the dot structure, for the bond line structure for this compound? I will draw this. So let's see what that means. That point is a carbon. Okay. Carbon is tetravalent. I am showing one bond to O. There must be 3 other bonds. Those 3 bonds are assumed to be to H's to complete the valence of the carbon. Therefore, that is a CH3 group. Here's my O showing its normal divalence. That point is a carbon. The carbon is shown with 1, 2, 3, 4 bonds. It has no other H's. That point is a carbon. It's shown with 2 bonds. But I know carbon is tetravalent. So there are 2 missing bonds. Those are assumed to be 2 H's. In other words, that's a CH2 group. That point is a carbon. It is shown with only 1 bond. It must have 3 more, assumed to be 2 H's. That's a CH3 group. By the way, CH3 groups are referred to as methyl groups. CH2 groups are referred to as methylene groups. Methylene. Right? So that's a methyl, CH3, that's a methylene. In a similar way, this is called methane. So I have methyl, CH3, methylene, CH2, and methane, CH. And that only applies to the carbons of the sp3 hybridized, by the way. Let's do a couple more. What does this convert this bond line structure into a dash structure? That is a carbon. That's a carbon. It is showing 1 bond, which means it must have 3 other bonds to H's. So that's a methyl group. That carbon is attached to another carbon, which is shown with 2 bonds, so there must be 2 other bonds to H's. In other words, that is a methylene group. That methylene is attached to another carbon, which is shown having 3 bonds, 1, 2, 3. So there must be another bond to an H, and I'm showing a double bond to a carbon. That carbon is shown as having 1, 2, 3 bonds, so there must be 1 bond here to an H, and then this bond to a carbon. That carbon is in a triple bond. So there must be a carbon here. So there's a carbon here, and a carbon here. So this is carbon, carbon. Neither of which will have H's because this carbon is now bound to another carbon, this one, which is bound to a carbon and a carbon, this one and that one. This is shown with 1, 2, 3 bonds. So there's a bond to an H. In other words, that's a methane, methanic carbon. And these are 2 methyls. So CH3, CH3. So this is the dash structure of this bond line structure. You guys will rewind the lecture as appropriate to catch up and go over stuff. Let's, if I have CH3, CH, let's say OH, C, double bond O, NH, C, H, H, C, triple bond CH. Let's convert this dash structure into a bond line structure. Pick a spot. Let's start here. I've got a method, right? That's my methyl. It's going to be attached to a carbon, which is methinic, so methyl and methine. So I'm going to go methyl up to my methine. It is attached to a carbonyl group, which is attached to a nitrogen having an H, a methylene, and a C triple bond C. And then this methine is attached to a carbon attached to an OH. Methyl, methine, CH2, OH, doesn't matter whether it's up or down, I'll make a point in a second. From the methine, carbonyl, C double bond O, attached to an N, H, CH2, C triple bond CH. Now you notice, while I show the H's bound to heteroatoms, I don't show the H's bound to carbon. When we draw bond line formulas, we want to be careful of two things. Typically when you draw them, and I'll bring some models in class next day so you can see, we draw them in a zigzag. So they go up, down, up, down, up, down, right? I may have drawn, yeah, see? Up, down, up, down, down. It's typical if you're going to have a group come off of an up carbon, like here, that the group goes up. In other words, it looks weird to draw that. Okay, that's kind of a no-no. If you have a group coming off of a down carbon, you draw the group coming down. Okay? The other point that's important with bond line is that if I know the shape for carbons that are sp2 or sp hybridized, I should show the shape in my bond line. What does that mean? Well, I know if I'm sp hybridized, I'm linear. Which means I have to draw this whole part in a straight line. Right? So it would be wrong to draw it like this. Oops. Right? That would be wrong. Because that tells me this bond angle is something other than 180 degrees. Or God forbid, draw something like this. Right? Because that bond angle is something other than 180 degrees. So when it's sp hybridized, you must draw it as if it's linear. When it's sp2 hybridized, you should draw it as if it's trigonal planar. And that's what I've done here. So I didn't show the H's, but if the H's were in, right, that is clearly a flat triangle. The only time it doesn't really count necessarily is when it's sp3 hybridized, right? Although in reality, like we did here, so that looks like if it's flat, and it's not. But when we get to stereochemistry, we'll make that point. Now, let me just say, if I ask you to draw the bond line formula for something, and you draw the shapes wrong, then it's wrong. Now, you won't get 0, but you won't get full points. Because if you know better, you're expected to do better. Okay? Let's do another one. So you remember when we're doing HDIs, we talked about benzene rings. And I was really kind of itching to get to this part because this takes some time. So what if we wanted to draw this in a benzene ring? What if I wanted to draw the bond line formula for that compound? Bond line structure. So I will do this. It's got the benzene ring, so I'm going to end up looking like this. I've got a carbon, right? And it's attached to 3 methyls. And then I've got an OH. I'm going to show the O attached, the H attached to O. I've got an N attached to an H and an OH. I've got an F, and I've got a C double bond O, OH. So that would be the depiction of that compound. And of course, this would represent a 3-membered ring. And so on, and so on, and so on. So I'm going to encourage you very strongly to practice this. I'll give you guys some practice problems because I'm going to be assigning sampling homework. You want to get accustomed to this because moving forward, these bond lines are the only ones you will see me use. So you want to be able to see the language and interpret what this species is. Let's talk about polarity. And you've met this in Gen Chem. And this would be, for you, it would be a recap of things you've met before, with a slight expansion, I think, when we get to molecular polarities. So we can divide polarity in 2 ways. So polarity can either be bond polarity, or it can be molecular polarity. And often people tend to refer to polarity as the moment of the molecule, the dipole moment of the molecule. So we can speak of the bond moment, right? And or you can speak of the molecular moment. The polarity of a bond is the consequence of a difference in electronegativity. So for example, if I have H attached to F, because the fluorine is more electronegative than the hydrogen, the sigma electrons in the HF bond drift towards the fluorine. They drift towards the fluorine, and I create a dipole. So I end up with one end of the molecule looking distinctly negative, one end looking distinctly positive. I could also represent that by saying there is a swell of electron density around the F, but a relative paucity of electron density around the H. Or I can say that the electrons in the HF bond drift towards the fluorine and away from the H. So all of these are equivalent depictions of the same idea. The electron pair in the HF bond drifts towards the F, because the F is more electronegative. If you want, the H is more electropositive and pushes them away. It's 6 1/2 dozen the other. That creates a negative dipole on the F, a positive dipole on the H. So we make 2 poles, it's dipoles. This would be an electron density map. There's a lot of electron density around the F, very little around the H. That's the same thing. Or that if I look at it right from an external perspective, the electrons are moving towards the F. And this cross in the tail tells me that end is delta positive. This is the positive end of the molecule. So the bond polarity is a consequence of the difference in electronegativity of the molecule.